All right, today we're cracking open the case file on one of the biggest mysteries in all of physics. Think of it as a cosmic detective story about why our universe seems to be playing by two completely different rulebooks. So let's get into it. Our investigation starts with, you guessed it, a cat. Schrodinger's cat, to be exact. See, in the quantum world, tiny particles can be in many places at once. It's called superposition. So the thought experiment goes, if a cat's life is tied to one of these quantum particles, couldn't the cat be both alive and dead until we look? But that's where the weirdness stops, right? In our world, things are one way or the other. Your keys aren't on the counter and in your car. So where is the line? Where does that quantum reality end and our everyday world begin? And that right there is the heart of the problem. We live in one single universe, but it acts like it's split down the middle, with two sets of laws that just don't seem to talk to each other. Over on one side, you've got the quantum realm. It is weird, it's wavy, and it's all about probability. An electron can be here, or there, or kind of everywhere at once. But then you have our world, the classical realm. It's solid, it's predictable, it's governed by certainty. A bowling ball has one location, and that's it, period. So the real mystery, the scene of the crime, if you will, is that transition. Where's the handoff? How big does something have to get before the universe basically steps in and says, nope, sorry, you gotta pick one state and stick with it? Well, our first major clue points to a suspect that's been hiding in plain sight this whole time. A force we know very well, a force that runs the entire cosmos. Gravity. Could gravity be the cosmic cop that enforces the laws of classical reality? Now, this idea actually has a name, the Diossi-Penrose model, or DP model for short, and the concept is just beautiful in its simplicity. It suggests that when a massive object tries to be in two places at once, it creates a superposition of two different gravitational fields, and apparently the universe just can't stomach that kind of situation, so it quickly forces a decision. And the logic here is pretty straightforward. The bigger the object, the more massive it is, the stronger its gravity. And the stronger its gravity, the more pressure it puts on the universe to snap out of that quantum weirdness and collapse into one single definite state. It's why a tiny electron can get away with being in multiple places, but a cat, or you, or a bowling ball, we can't. But here's the twist in our detective story. The DP model is a fantastic lead, but it's not the whole story. It tells us what happens. Gravity makes things choose, but it never explains how. I mean, how does gravity even know an object is in two places at once? What's the actual physical mechanism at play? It's like having a suspect and a motive, but no murder weapon. The case is still cold. So, to find that weapon, our investigation has to look somewhere really, really unexpected. The next clue isn't in a particle, it's not in a force, it's in a place we usually think of as total, absolute nothingness, the vacuum of space. You see, a newer theory called vacuum pulsation curvature theory, let's just call it VPCT, proposes that the vacuum isn't empty at all, not even close. Instead, you should picture it as a dynamic, buzzing, active cosmic fabric. And this fabric isn't just some boring background, it's where all the action is really happening. So check this out, here's how it's supposed to work. In this VPCT model, any object with mass is like a bowling ball sitting on a trampoline, creating a dent in that cosmic fabric. That dent, that curvature, that is gravity. Okay, now imagine an object in a quantum superposition, trying to be in two places at once. That means it's trying to make two separate dents in the fabric at the exact same time. Well, the fabric just can't handle that. It can't have these two competing, contradictory dents. It gets unstable, and it's forced to choose one, relaxing into a single, stable dent. That physical process of the fabric relaxing, that is the collapse from quantum to classical. So, to put it a bit more formally, VPCT says that everything, gravity, mass, quantum weirdness, all of it comes from this one single complex vacuum field. And the collapse we've been hunting for isn't some abstract magic trick. Nope, it's a real physical process of this cosmic fabric sorting out an impossible, unstable state. Now, this is the really crucial part. VPCT isn't trying to replace the old DP model, it's trying to complete it. DP was the detective who identified gravity as the prime suspect. VPCT is the forensic expert who comes in and says, I found the weapon. It provides the how, that physical instability in the vacuum field. It's the missing piece of the puzzle. Okay, but this is where our detective story gets really good. This is where it leaves the world of theory and enters the real world. Because this new, more complete picture isn't just a cool idea. It gives us something incredible, a way to actually test it in a lab. Unlike so many big, grand theories in physics, VPCT doesn't just offer up a nice story. It gives us a smoking gun, a hard numerical prediction that we can go out and test. And what that means is experiments are either going to prove it right or prove it wrong. There's no hiding. And here it is. This is the prediction. VPC says there is a hard and fast size limit to quantum weirdness. According to this theory, absolutely nothing larger than about 100 nanometers in diameter, we're talking the size of a virus, can exist in a state of spatial superposition. Now, to put that into perspective, that size corresponds to a mass of about 10 to 100 million atomic mass units. That's the unit scientists use for things on an atomic scale. VPCT says that once an object gets that heavy, the instability it creates in that cosmic fabric is just too much to handle. The collapse isn't just likely, it's immediate and unavoidable. So this sets up this incredible scientific showdown. Standard quantum theory, it says there's no limit at all. You could theoretically put a bowling ball in two places at once. The original DP model, our first suspect, predicted the collapse would happen, but way later, around 1 billion atomic mass units. But VPCT draws a much sharper line in the sand. It says the collapse happens much, much sooner, at just 10 to 100 million. And that huge difference in predictions is exactly what makes this theory so powerful, because it means we can actually test it. Okay, that is a fantastically precise prediction. So how on earth are scientists actually planning to test this? I mean, how do you carefully nudge an object right up to the very edge of the quantum world without breaking it? Well, it turns out there is a whole squad of incredible experiments closing in on this very mystery. You've got major projects like MassQG, proposed space missions like Macro for even better sensitivity, and even these super clever techniques using lasers to trap and cool tiny nanoparticles. They're all using different tactics, but they have the exact same goal: create a superposition of a bigger and bigger object and push it right into that critical window to see what happens. And the stakes just could not be clearer. There's a quote from the source material that lays it out perfectly. If an experiment like MassQG manages to put an object with a mass of 1 billion atomic units into a superposition, then VPCT is wrong. Case closed. But if they see that quantum weirdness just vanish as the object approaches that 100 million mark, well, that would be incredibly powerful evidence that VPCT is on the right track. And this, for me, is the most exciting part of this whole story. The answer to this deep, fundamental question about the very nature of our reality isn't just for philosophers or theorists anymore. A verdict is coming, and it's going to come from real, hard, experimental data. You can kind of think of it like this. We understand the huge territories of the quantum world and the classical world pretty well on their own, but it's this tiny sliver of an unexplored border between them. That's where the next great revolution in physics is waiting for us. So the final question is a pretty thrilling one, isn't it? After a century of wandering and debating, are we on the verge of finally drawing the map? Are we about to get a real experimental answer for where the weirdness ends and our solid everyday reality begins? The experiments are running, and the universe's secrets might not stay secret for very much longer.